let me remind you that we have our final, our second midterm, which will be our last midterm, last exam before the final, will take place Friday, right before spring break in class, 9 to 10 a.m. Bring paper and because it's going to be on campus just like it was before, you'll have to upload it no later than 10:05 p.m. or a.m. And we have a review session Wednesday in Long 216, 7 o'clock. Okay, any questions? Okay, so this is a theorem that we were talking about last time. This is a so-called Lagrange's theorem. And basically what it says is if you have a group with n elements in it, whatever the n has to be, if you've got a subgroup, then the number of elements in the subgroup divides the number of elements in the group. So there's a certain symmetry going on there. So for example, if you have a group of 100 elements, then your possibility for subgroups, you got a subgroup of order 50, 20, or 25, but you can't have a subgroup of order 15 because it doesn't divide 100. The same is true for the order of an element, because actually the order of an element, it turns out, is the same as the order of the subgroup that it generates. And this last mysterious thing, this quotient, G divided by the order of the subgroup, this is exactly the number of left cosets. And we talked a little bit about cosets last time, so let me go over an example again, and we'll actually see Lagrange's theorem in action before we actually show it's true. So we did some examples yesterday with the integers, and, or last time with the integers in S3. Let's look at an example of cosets in Z6. Let's let H. Okay, so what I want to do is I want to look at the left cosets of this particular H. Notice this subgroup H has 2 elements, and the whole group has 6 elements. So I've already got part of Lagrange's theorem, right? The order of the subgroup divides the order of the group. Notice we've been over this kind of example before. The order of these elements are 6, or I'm sorry, the orders of these elements are 1, 6, 3, 2, 3, and 6. Notice all the orders of the element divide the order of the group, right? Now let's look at the cosets. Let me start off with the coset. How about, notice I wrote my cosets before it's multiplication, but here I'm adding it. It's all right this way. This is just translating everything by 0. 0 bar plus 0 bar is 0 bar. 0 bar plus 3 bar is 3 bar. That was easy. Notice that this is the same coset as 3 bar plus H, because when you take everything in H and add 3 to it, you get the same set of elements, right? Because 3 plus 0 is 3, and 3 plus 3 is 0. Everyone cool with it? Okay. Give me another element in the group. Not 0, 3. Okay, how about 4? Why not? Let's see what this one is. Well, let's see. 4 bar plus 0 bar is 4 bar. 4 bar plus 3 bar is 7 bar, which is back to 1 bar. So let's see. Let's look at the elements that we've seen so far. We've seen a 0, a 3, a 1, and a 4. Colton, give me an element I haven't seen. 2. Okay, how about 2? Notice this is also the same thing as 5 bar plus H, right? Because I can use any representative of the coset. Now, notice what we have here. These cosets, these left cosets, notice when I've gone through 3 of them, I've gone through all the elements of the group, right? Every element of the group is in one of these 3 cosets, right? And there's no overlap between the 2 cosets, right? 0 is here and only here, 1 is here and only here, and so forth. So there's no overlap between different cosets. This is kind of an important thing. Let's look at this last bit here. The number of left cosets is the order of the group divided by the order of the subgroup. So let's see, what do we got here? Order of the group is 6, order of the subgroup is 2, quotient is 3, and there you go. 1, 2, 3. Everybody okay? Okay. So let me give you this theorem. And this will be a very important theorem, sort of doing our counting here. And this theorem sort of, I like doing this example first because this theorem really goes hand in hand with this example. It's a generalization of this example. Let G, we're ready, 5, 3, 4. Let G be a group. And H and G. We define a relation on G by declaring X is related to Y if and only if Y inverse X is in H. So I'm going to say that X and Y are related if Y inverse X is actually an element of the smaller subgroup. Like over here, this example here, we would say that, for example, 0 and 3 are related because 0 minus 3, which is 3, is in the subgroup H. Right? However, 1 and 2 are not related because 1 minus 2, which is -1 is 5, is not in here. Right? And this actually forms an equivalence relation. This is actually an equivalence relation on G, and the equivalence classes are the set of left cosets. Yes.
Sorry, this might be a dumb question, but why are there 2? Why is it required to have 2 elements for every subset from the last example?
In this example, what do you mean 2 elements from every subset?
For each of the cosets.
Oh, well, because the original group has 2 elements in it. I just kind of picked that subgroup at random, right? And so any coset, for example, 0 plus H is going to be 0 plus this, 0 plus that. So it's going to have 2 elements. Another coset, 4 plus H, is going to be 4 plus this, 4 plus that, so 2 elements. Did that address the question? Or did I miss it?
So they're all based off of some reference group.
That's right, some pre-picked group, subgroup.
Okay, sorry.
Then this is an equivalence relation on G, and the set of equivalence classes the set is, yes, precisely the set. this is actually an important observation, and we're going to use this because we do know the big thing that we know about equivalence classes of equivalence relations is when you have an equivalence relation on set, the equivalence classes break it up into the puzzle pieces, the partitions, right? So let's see why this is true. This is kind of an important thing. Okay, the first thing that I've got to establish here is I've got to establish that this is actually an equivalence relation, right? So I need to show it's what? Reflexive, symmetric, and transitive, right? Well, let me point out that E is an H, right? Looks like I'm coming out of nowhere here, but H is a subgroup, so it's got the identity. Agree? And I don't know much, but G. I can write an identity this way. So what does this mean? This means for every X in G, X inverse X is in H, right? So X is related to X because X inverse X is the identity which is always in H. So it's reflexive. Everybody agree with that? How about symmetric? Well, suppose X is related to Y. This means that because that's what we said. This is what the rule is. Now I need to show that Y is related to X, right? We've seen that relations don't have to be symmetric. We have that X is related to Y. We need to show Y is related to X. So I guess we need to show sort of the opposite. We need to show that X inverse Y is actually an H. You want to tell me why this is true?
Doesn't matter what
You're close. You can't just flip them around because the operation of the group may not commute. But what do I know about H? It's a subgroup, right? So H is a group unto itself. And I know that this animal lives in H, right? And H is a group the inverse of that thing also has to be an H, agree? And what's the inverse of this? So, wow. There we go. So it's symmetric. Okay. How about transitive? I think actually symmetric is probably the hardest one for this one. Well, what does this mean? This means that Y inverse X and also Z inverse Y is in H. Everybody agree with it? Now, somehow I need to show X is related to Y, Y is related to Z. I need to show that X is related to Z. So any ideas on how I do that? Yeah, that's what I mean, at the end of the day, we need to show that X is related to Z, right? So we need to show that Z inverse times X is in H. You see any way that I can?
Multiply them together.
There you go. This is a subgroup. So when I take this animal times this animal, it has to be in there. I love subgroups, right? And what happens to the y inverse? Poof, Casper, they're gone.
Like a group, you can, I guess, multiply or do the operation of any two elements, and it's also in the group.
That's exactly right. That's very important. Yeah, the closure, if you will. So. There we go. Okay, so we got that part of it. Like, so this is an equivalence relation on G. Yay. And so now we have to show that the set of equivalence classes is precisely the set of left cosets of H and G. Well, okay. So the strategy for the rest of it is I'm going to do this. I'm going to take equivalence class and I'm going to show it's a left coset. Then I'm going to take a left coset and show it's an equivalence class. Okay. So first of all, let X be in G, and the equivalence class of X. Let me remind myself what this is. This is all the crap in G, such that G is equivalent to X. So we'll see, I need to upgrade this a little bit. So this is the set of G and G such that X inverse G and H. Okay, what does that mean? This is the set of G and G such that X inverse G is equal to some little H in H. So I have never really, I just kind of did this little notation here. Maybe this will help me. X inverse G always has to be some little H in H. And so this is the set of G such that G, so multiply this on the whatever side this is, left side by X. Right? Because if X inverse G equals H, it's the same thing as saying G equals XH. So it's a left coset. Because really, remember what a left coset is? In fact, it's a left coset with representative X, right? Because it's X times H, where H runs through all the elements of the left. Am I okay? So what I've shown here is any equivalence class is a left coset. Now, I want to get the opposite for you. That is that any left coset is an equivalence class. Now, suppose that we have a left coset I claim that we get equality. And actually, in the previous one, I've already shown this equivalence class is contained in here, but I claim that XH is equivalence class. So to this end, this is a set of every two-letter combination I can make where the first letter is X and the second letter is something in H, right? Think of it that way. Which is, such that G so this is just a rewriting of this. It's every element of G of this form, where H is an H, which is the set of G and G, such that X inverse G, which is set of G and G, such that which is the set of G and G, such that G is equivalent to X. And then, so this theorem is established. This notion right here is in fact an equivalence relation, and the equivalence classes are precisely the set of left cosets. Now, I'm going to give you this corollary, and this corollary is just an observation. In fact, maybe the corollary is even more important than the more generally stated theorem. And then when we do the corollary, we'll have everything set in place for us to establish that Lagrange theorem works. Let G be a group and H is subgroup. Then the set of left cosets of H and G partition G. Now remember what we mean by partition. G is a giant puzzle, and a partition is just breaking it up into puzzle pieces. When you put all the puzzle pieces together, you get all of G back, and no two puzzle pieces, no two different puzzle pieces overlap. So let me draw you a picture of what we've got so far. Here's G. What we said so far is the set of left cosets partitions G into puzzle pieces like this. Right. Notice I've got 6 puzzle pieces there. Left coset, left coset, left coset, left coset, left coset, left coset. There's no overlap, and when you put them together, you get all G. But there's even more to this particular. This is what you could imagine that the puzzle pieces look like, but they're so much better than this. So what is more, for all X and G, so all left cosets are of the same size. Notice how the way I've drawn this initially I mean, I couldn't assume until this point that all my left cosets are the same size, but they are. So not only does this break this up into puzzle pieces, but they're all the same size. So a more accurate picture might be something like this, where all the left cosets actually are the same size. Maybe this one is H, and this is XH, like this.
Why can we not assume that they're all the same size?
Well, so for example, because partitions can be anything, so let me give you kind of a silly example. The reason you can't assume it at the outset is one way, if I take a set of 5 things, or let me take a set of these things here. 1, 2, 3. So a partition of this might be 1, 2, 3, 4, 5, 6, 7. I mean, that's a perfectly legal partition, right? I've got 4 puzzle pieces, got a couple small ones, a medium one, a big one. There's no overlap, right? So in your worst nightmare, you might think, well, maybe this is what happens with cosets, but it doesn't. For our cosets here, all of them break up into the same size, and I'll show you why that's true. Proof, since my cosets in these classes they form a partition. This is why this is a corollary from the previous one, because I've already shown that the left cosets actually form equivalence classes, and we already know that equivalence classes form a partition. So this statement up here, we already knew that from the previous theorem. This is really what requires justification, is the question about why they're all the same size. We only really care about finite groups, finite cosets, but I'm going to give you a proof that works whether the cosets are finite or infinite. It turns out even if these are infinite cosets, they have the same size. So we now show these 2 cosets are the same size, and by transitivity, that means any 2 cosets are the same size. Because, for example, if you want to show that the coset XH and the coset YH are the same size, remember, XH is this size and YH is this size, so XH and YH. Everybody okay? By the way, again, I'm not assuming this is finite, so any ideas on how we show these 2 things are the same size? Quickly answer me. Remember, are there more people in the room here or more slats over there? There's more slats, and you answered that really quickly. The pairing off idea. What I'm going to do is I am going to see if I can pair these off. So I'm going to define a function f from h into xh. Now remember, this is math, so if it ain't easy, don't do it. So I'm going to find this function from the subgroup H to this left set left cosets. Now, remember, my input is going to be something from H, and my output better be something that looks like X times H. What's the easiest way? See, it better be X times something, because it's in XH. What should I put in the blank here? H, right. Again, if it ain't easy, don't do it. Now, what I want to do is I want to show that this function is a bijection, right? It's 1-to-1, it's onto, we paired everybody off, and then we're all happy that they're the same size, right? So I need to show right from our counting, this is what we want to do, is to show these things are two sides, same size, show it's a bijection. So okay, show it's 1-to-1 out. Okay, so 1-to-1. Do 1-to-1. So let's suppose H1 and H2 give the same output, right? We got to show that the input is the same. That is, we need to show that H1 and H2 are the same, right? Okay, what does this mean for them to get the same output? This means that X, H1 equals X, H2. Agreed? And now you gotta love groups because every element has an inverse. So what I want to do is I'm going to multiply on the left side by X inverse. Examples, these two becoming identical. So, okay. Same output means same input, so it's 1-to-1. How about onto? Onto, actually, in this case, might be a little bit easier. What does it mean to be onto? It means nobody is lonely over in XH1. Everybody's got a dance partner. So what does a typical element of XH look like? What does a typical element of XH looks like? It looks like X times something, and that something's got to be an edge. Agree? Somebody tell me what magic element of H goes to this? Nothing so fancy, just H, right? F of H equals XH. This thing is an H. So, yeah.
Why did you choose H there?
Because that's the way my function works. This was, remember, this is the rule.
Oh, right.
So I just read whatever's here and put it there. Yes.
So are you saying that it's onto from the initial definition that it covers all of it?
That is correct, because an arbitrary element of what's over here is of this form, right? And once I know what this form is, I know what to cover it with. But, so this function from H to XH is 1-to-1 and it's onto. So F is a bijection. And so they're the same size.
So the first part, when what just shows that we can't have, to say that we want H1, H2 are they're the same, so you can't have any duplicates or anything.
Right. What this shows is that can't happen. That's what that shows. This situation cannot happen.
And why does the second one prove that it's onto?
Well, because what it needs to be onto is pick somebody over here. We don't want this person to be lonely. We want them to have a dance partner. Okay, what do I know about this person? This person lives here, right? So what do I know about this? I know that this person is an X little h. Now, does my function assign a dance partner to this? You bet it does, because my function takes h to xh. And so everybody's happy. Yes.
So the reason that this proves that this function being a bijection is of the same size is because the input and output must be, or the domain range must be the same.
Right, so what, yeah, it means the domain and range are the same size, because essentially what this means is, so this is kind of intuitive, but I think intuitive's good. So this is a finite picture, but this works for the infinite too. When we say it's 1-to-1, so we've got some folks here. When we say it's 1-to-1, we say this can't happen, right? No two people are jealously trying to get the same dance partner. Everybody gets a different dance, right? And this one right here says that nobody over here is lonely, right? Agree? That means everybody over here, somebody likes them. And no two can go to the same place. Notice if you have one more here, then somebody's going to be lonely on this side. It's not going to be on to it. Notice if you have one more here, then two people are going to be trying to dance with the same person. Right? So, in other words, that's why we went over that stuff with functions and the bijections pairing off. A bijection means that you can pair off the elements of the set, and that's what we mean to be same size. Okay, good, good. Other questions? Okay. All right, so now we've got, what do we have? We have all the left cosets are the same size. We know they form a partition. Now we've got Lagrange's theorem. We're totally going to conquer this thing now. Suppose G here in finite group. And the order of G, same thing. So it's got n elements in it. Now let H be a subgroup of order n. Of course, a big part of proving this is showing that n divides n. So that's part of the statement of Lagrange. So let me actually, I'm going to do this also over on this board. This will kind of help, I think, in the exposition of this. Now here's G, right? It's got n elements in it. And here's what H looks like. Right? It's a subgroup of order n. Right? Notice, by the way, H is also a left coset as well, right? It's H is the identity times H, right? So it's a coset just like the rest of our friends. The left cosets of H and T G. Since G is finite, there are only finitely many cosets. Right there, well, let me see, left. Right, because there's only finitely many things in G, and there's finitely many things, there's at least one thing in H, agree? I mean, even if H is only the identity subgroup, it's only got one, then there's at most n cosets, right? Because notice, every coset contains at least one element of G, right? I don't know much, but I know since there's only n elements of G, once I've got n of those small boxes, for sure that's going to be probably too much, but it's going to be at least as big as G is. Do I agree with that? So in particular, there's only finitely many left cosets. Everybody agree with that? So let me call them something. So let's list them. I'll be convenient. XKH. Right. Now, let's collect some facts here. What do I know? I know G is X1H union X2H union. This is part of our partition thing, right? These are my puzzle pieces. Right? So maybe this is X1H, X2H, and finally XKH. Okay. Now, this means the origin is, now remember, this is important. How do we count up elements of subsets when they're disjoint? Just add them up, don't we, right? Because there's no overlap between the cosets. We can just straight up add them up. So if I wanted to count the elements in G, just count these and then count these and then count until I'm finished. So this is just add them up. Now, notice that by the previous corollary, all of these things have the same size as H. And how many times is this? Well, there's one H, two H, all the way up to KH's. So the order of G is K times the order of H. So the order of H divides the order of G, right? Because the order of H times an integer is the order of G, and the order of G divided by the order of H is K, which is the number of that coset. Because this, remember, that's our exhaustive list of left cosets, and there are K. Any questions? This is an incredibly important counting theorem for groups, and this will actually serve us later when we look at some applications of group theory. Let me also point out, I've got it listed separately as a corollary, but this also is true that if you have an element in G, then its order, the order of the element divides the order of the group as well. And that's because the order of the element is the same thing as the order of the subgroup that generates. Of course, it's natural to ask, and I mentioned this, but I feel obligated to mention then. So question. This is a natural question to ask. If the order of G is n and n divides n, does G have a subgroup? And the answer is not necessarily. Maybe, maybe not. I am going to give you right. I'm going to give you a theorem here. And the proof of it is beyond, it's not terrible, but you need to know a little bit about group actions. That's the easiest way to do it. And so I'm not going to prove it here, but you can use it. But this is a theorem, very famous theorem by Cauchy. And number first 5 through 7. If G is a group order and E is a prime, so 0 is a prime number such that divides in, then G has a subgroup of order so if you have any group of order n, if you have a prime that divides, in, then you automatically have a subgroup and hence an element of that order in G. And I'll take this is further than what Cauchy tells you. I'll tell you this more general theorem. Unnumbered. If G is a group of order n and A divides A prime and K greater than 1, then G has subgroups of order E to J. So let me kind of give you a quick example to show you what I mean by that. So for example, if order G is 324, right, which is 2 squared times 3 to the 4. If you have a group like this, then G has four, 3, 9, 27. Right. So it has subgroups of every prime power that divides the order group. And also in the certainly the subgroup order 1, the identity, and it's got a subgroup order 324. The whole group. But beyond that, it's not really clear, right? So does this have a subgroup order 6? I don't know. It may depend on what the group is. Okay, any questions? questions on that? Questions on this stuff? All right, put that in your pipe and smoke it. See if you can, if there's any difficulties, come give me a holler and I'll help you out. Let me say, I know you guys are kind of getting your sea legs with this. I expect the average on this homework, I'm almost done grading. I've got a few more to do. But the average on this is a little bit lower, so make sure that you look at it, understand anything that's gone already for you, and I will help you out with that. Other than that, we will see y'all next time.